So the next speaker of this session is Alexander Campbell, and he will speak about Joyal's cylinder conjecture. Please go on.
Thank you very much, and thanks to all the organizers for their Herculean efforts, which have made this conference such a great success, and for bringing us all together across the world. So today I'm going to tell you about my recently published paper in which I prove a conjecture of André Joyal in quasi-category theory, which I've called Joyal's cylinder conjecture. This talk will be in 3 parts. In the first, I'll give background to and the statement of Joyal's cylinder conjecture. In the second part, I will outline my proof of this conjecture. And in the third part, I'll say a few things about the hard part of the proof. So first, the background and the statement. So first, what's a cylinder? So let A and B be a pair of simplicial sets. We define a cylinder from A to B to be a simplicial set equipped with a map of simplicial sets to delta 1, that's the free-living 1 simplex, whose fibers over the 2 vertices 0 and 1 are A and B respectively. I invite you to think of a cylinder from A to B to be the model of a profunctor from A to B in quasi-category theory, or better yet, the model of the collage of a profunctor from A to B. Now, cylinders from A to B form a category, which I'm calling Sil AB, the morphisms in which are maps of simplicial sets over delta 1, which restrict to identities on the fibers. Now, it's important to note that the terminal object in this category Sil AB is the join of A and B. This is some combinatorial operation on simplicial sets. I've given a few little formulas below, but just think about it as the collage of the terminal profunctor between A and B. So as the terminal object of this category, there is for each cylinder X in Sil AB a canonical map of cylinders from X to the join of A and B. And these will feature in the statement of Joyal's conjecture. And this conjecture concerns a certain model structure on the category Sil AB. So let's recall what model structures are. So the standard slogan is that a model structure on a category enables one to do homotopy theory in that category. Precisely, it consists of 3 classes of maps called weak equivalences, cofibrations, and fibrations, subject to various axioms. And we say that a category equipped with a model structure is a model category. Now, an object in a model category is said to be fibrant if the unique map from it to the terminal object is a fibration. Now, a model structure consists of these 3 classes, but it's completely determined by certain proper subsets of that data. For instance, a model structure is completely determined by its cofibrations and its weak equivalences. The fibrations are then, by the axioms, precisely those maps with the right lifting property with respect to those maps which are both cofibrations and weak equivalences. Alternatively, a model structure is completely determined by its cofibrations and its fibrant objects. So if I have 2 model structures on the same category which share the same class of cofibrations, then they are equal if and only if their classes of weak equivalences are the same, if and only if their fibrant objects are the same. And there's a kind of contravariant relationship here. If I fix the cofibrations, the more weak equivalences there are in my model structure, the fewer fibrant objects, and vice versa. Now, the most important model structure for us to recall is Joyal's model structure for quasi-categories on the category of simplicial sets. So recall that a simplicial set is said to be a quasi-category if it has the right lifting property with respect to all inner Horn inclusions as displayed. And more generally, we say that a map of simplicial sets is an inner fibration if it has the same right lifting property with respect to all inner Horn inclusions. Now, there is this model structure on simplicial sets whose cofibrations are the monomorphisms and whose fibrant objects are the quasi-categories. And as we said before, this completely determines the model structure. The name that I'll use for the weak equivalences in this model structure is categorical equivalences. And I should say a few things about the fibrations in this model structure. So it's true that every fibration is an inner fibration, but the converse is not true in general. For a map between quasi-categories, we know that it's a fibration if and only if it's a so-called isofibration, it's an inner fibration which has an additional isomorphism lifting property. But it's important to note that we do not have any such nice description of the fibrations between arbitrary simplicial sets. And it's this fact which makes the proof of this Joyal conjecture difficult. Okay, so now to model structures for cylinders. So let's again fix a pair of simplicial sets, A and B. there's a forgetful functor from this category of cylinders from A to B to simplicial sets, which simply forgets for each cylinder the map down to delta 1. And one can show that there's a unique model structure on Sil AB created by this forgetful functor from the model structure for quasi-categories on simplicial sets. That is to say, a map in Sil AB is a weak equivalence cofibration or fibration in this model structure, if and only if its underlying map of simplicial sets is a weak equivalence cofibration or fibration, respectively, in Joyal's model structure for quasi-categories on simplicial sets. Now, I'll call this model structure on Sil AB the Joyal model structure on Sil AB. Okay, and Joyal's conjecture concerns the fibrant objects in this model structure. By definition, a cylinder X in Sil AB is a fibrant object in this model structure, if and only if that canonical map from X to the join of A and B is a fibration in the model structure for quasi-categories on simplicial sets. Now, as I said, we don't have a nice description of these fibrations in general, but Joyal conjectured that in this particular case, we do have a very explicit description of when such a map is a fibration. Namely, he conjectures that a cylinder X in Sil AB is a fibrant object in this model structure, if and only if that canonical map from X to the join of A and B is an inner fibration, and that's all, no further conditions required. And there's a second half to this conjecture, which states that a map between fibrant cylinders in Sil AB is a fibration, if and only if it's an inner fibration. So that's Joyal's cylinder conjecture. Here I have stated it again, but emphasizing that the conjecture states that this is true for all pairs of simplicial sets A and B. Now, because we have that nice description of fibrations in the model structure for quasi-categories between quasi-categories, it is the case that for the special case of Joyal's conjecture in which A and B are quasi-categories is very easy to prove. Here's how it goes. So I've stated this as a lemma. So we suppose that A and B are quasi-categories. Then in the Joyal model structure on Sil AB, the conclusion of Joyal's conjecture holds. So, namely, that an object is fibrant if and only if the canonical map to the join of A and B is an inner fibration, and that a map between fibrant objects is a fibration if and only if it's an inner fibration. And in the proof here, I've given the non-trivial direction of the first half. So we have our map from X to A star B, the join of A and B. We suppose it to be an inner fibration. And we want to show that it's a fibration in the Joyal model structure. Well, by assumption, A and B are quasi-categories, and hence so is their join. And so we've got a map, an inner fibration between quasi-categories that we want to show is is a fibration in Joyal's model structure. It suffices to show that it has the isomorphism lifting property. But the only isomorphisms in the base, A star B, are those that belong to the subcategory A or the subcategory B. And the fibers of this map over those subcategories are just A and B themselves. And so there's a unique lift of every isomorphism, in fact. So that's the background to and the statement of Joyal's cylinder conjecture. It's something which we conjecture holds for every pair of simplicial sets A and B. And we've seen that it's very easy to prove in the case when A and B are quasi-categories. So I'll now outline my proof of the general case. And as you might expect, we prove this by reducing it to the special case. And here's how that argument proceeds. So I'll outline this proof in 5 steps. So in the first step, we construct for each pair of simplicial sets A and B a new model structure on Sil AB, which I call the ambivariant model structure for reasons I won't get into, which by design, by construction, satisfies the conclusions of Joyal's conjecture. Namely, as I said in this theorem, it is this unique model structure on Sil AB whose cofibrations are the monomorphisms and whose fibrant objects are exactly those cylinders described in Joyal's conjecture. They are those cylinders X in Sil AB such that the canonical map from X to the join of A and B is an inner fibration. And one can show, moreover, that the fibrations between fibrant objects in this ambivariant model structure are precisely as in Joyal's conjecture. They are the inner fibrations. So that's the first step. And so our second step is merely to observe that, well, Joyal's conjecture is now equivalent to the statement that for each pair of simplicial sets A and B, these two model structures on Sil AB, the Joyal model structure and the ambivariant model structure, coincide. We have this thing we want to prove about the Joyal model structure. We know it's true of the ambivariant model structure by construction. And so if they coincide, then Joyal's conjecture holds. And the converse direction is also easy to see. In particular, in the case when A and B are quasi-categories, we know that these two model structures do coincide. So now our task is to show that these two model structures coincide. And well, they're two model structures on the same category, which have the same class of cofibrations, namely the monomorphisms. And so to show that they coincide, it suffices to show that their classes of weak equivalences coincide. I'll call the weak equivalences in the Joyal model structure the categorical equivalences, and I'll call the weak equivalences in the ambivariant model structure the ambivariant equivalences. Now, one direction is easy. It's easy to see that every ambivariant equivalence is a categorical equivalence. This is because of that contravariant relationship that I mentioned earlier. It's easy to see that every fibrant object in the Joyal model structure is fibrant in the ambivariant model structure. And this is just by definition from the fact that every fibration in the model structure for quasi-categories on simplicial sets is in particular an inner fibration. And so it remains to show the converse direction, namely that every categorical equivalence is also an ambivariant equivalence. And here's how we do this. So we're going to utilize a change of base operation. So we want to make this reduction from the general case to the case where the ends of our cylinders are quasi-categories. And we use this push-forward operation. So given a pair of maps of simplicial sets, U from A to C and V from B to D, we get this push-forward functor going from sil AB to sil CD, defined by this push-out square of simplicial sets displayed. And we prove two technical properties of these push-out functors. Firstly, these push-out functors always preserve categorical equivalences. That's easy to prove. The thing that's very hard to prove, and this is the core difficulty in the proof, is that if we push forward along a pair of categorical equivalences of simplicial sets, then that push-forward functor reflects ambivariant equivalences. That is, if I've got a morphism in sil AB, whose push forward along a pair of categorical equivalences is an ambivariant equivalence, then it must have been an ambivariant equivalence to begin with. And that's as I've said, the hard part of the proof. But once we have that, it's straightforward to argue to prove what we want, which is that the categorical equivalences are in particular ambivariant equivalences. So we start with our pair of simplicial sets A and B, and we take fibrant replacements of both of them in the model structure for quasi-categories on simplicial sets. That is, we have two maps, U and V, which are both categorical equivalences and whose codomains, C and D, are both quasi-categories. We take a morphism F in sil AB, we assume it's a categorical equivalence in sil AB, and we want to show that it's an ambivariant equivalence in sil AB. First, we push forward along this pair of categorical equivalences, and since push forward always preserves categorical equivalences, we know that the push forward of F is a categorical equivalence in sil CD. But C and D are quasi-categories, and we observed earlier that the Joyal model structure and the ambivariant model structure coincide in that case. Hence, our categorical equivalence in sil CD is also an ambivariant equivalence in sil CD. But we've pushed forward along a pair of categorical equivalences, and push forward along a pair of categorical equivalences reflects ambivariant equivalences, and hence our original map is an ambivariant equivalence, which is what we wanted to prove. And this completes the proof. By this argument, we've shown that for each pair of simplicial sets in this Joyal model structure on sil AB, an object is fibrant if and only if that canonical map to the join of A and B is an inner fibration, and moreover that a map between fibrant objects is a fibration in this model structure if and only if it's an inner fibration. That's the outline of the proof. So in the time that I have remaining, let me say a few things about the difficult part of the proof, which was that second half of step 4, that push forward along a pair of categorical equivalences reflects ambivariant equivalences. Okay, so this part of the proof amounts essentially to an analysis of these ambivariant model structures that we defined. So we begin with an observation of Joyal, which is that for each pair of simplicial sets, A and B, the category of cylinders from A to B is a presheaf category. It's equivalent to the category of presheaves over the Cartesian product of the categories of simplices of A and B, as displayed. Now we can go further. Combining the standard equivalence between the category of presheaves over the category of simplices of some simplicial set B with the category of simplicial sets over B yields the following equivalence between sil AB and the functor category. displayed, the category of contravariant functors from the category of simplices of A to the category of simplicial sets over B. Now, under this equivalence, the ambivariant model structure on SIL-AB must correspond to some model structure on this functor category. And what we do is give a nice description in terms of that functor category of that model structure. And so we'll do that using the following structures. So first, for any simplicial set B, there is on the category of simplicial sets over B a model structure due to Joyal called the covariant model structure. It's uniquely determined as the one whose cofibrations are the monomorphisms and whose fibrant objects are the so-called left fibrations with codomain B. These are the quasi-categorical analogues of discrete op fibrations. And I call everyone calls the weak equivalences in this model structure the covariant equivalences. Another structure we'll need are just these final vertex inclusions, which are certain maps of simplices. So for each natural number m, in this category of simplices, there's the final vertex inclusion, which just picks out the final vertex. And similarly, in the category of simplices of any simplicial set, there is this class of final vertex inclusions, one map for each simplex in the simplicial set. So using these two things and various standard constructions and notions from model category theory, I can describe the model structure on this functor category, which corresponds under this equivalence to the ambivariant model structure on SIL-AB as follows. So let me just say this. So under this equivalence, the ambivariant model structure on SIL-AB corresponds to the Bausfield localization of the Reedy covariant model structure on that functor category with respect to the final vertex inclusions. So let's say that in the other direction. So we have this covariant model structure on simplicial sets over B. We also have the category of simplices of A, which is a Reedy category. It inherits a Reedy category structure from the standard Reedy category structure on the category of simplices. Those two things together give a Reedy model structure on that functor category with respect to the Reedy model structure on the category of simplices of A and this covariant model structure on the category of simplicial sets over B. We now perform this further operation of localizing this model structure with respect to these final vertex inclusions. So for those of you who knows what this means, the local objects in this Bausfield localization are those functors from those contravariant functors from the category of simplices of A to the category of simplicial sets over B, which send all final vertex inclusions to covariant equivalences. Now the proof involves various things. Let me just mention one, which is a result of Danny Stevenson, which characterizes the class of right anodyne extensions of simplicial sets, which are involved in the definition of these covariant model structures, in terms of the final vertex inclusions. Very useful result. And so we use this theorem together with a theorem of Joyal, which states that push forward along a categorical equivalence preserves and reflects covariant equivalences. This is a very deep theorem, very difficult to prove. So using these two things, we prove this difficult step of the proof of the Joyal conjecture, namely the push forward of cylinders along a pair of categorical equivalences reflects ambivariant equivalences. And so that's my little summary of what goes into the difficult part of the proof. Now I have one final thing I would like to say, which is the following. So in the proof of Joyal's conjecture, we constructed this other model structure, the ambivariant model structure, which we showed coincided with the Joyal model structure from which we deduced the conjecture. But in particular, everything that we proved along the way about the ambivariant model structure is true also of the Joyal model structure. So in particular, we have that theorem from the previous slide saying that under that equivalence, now the Joyal model structure on SIL-AB corresponds to that Bausfield localization of this Reedy model structure on that functor category. And as it happens, it's actually this corollary to Joyal's cylinder conjecture which I found more useful rather than Joyal's cylinder conjecture itself. My interest in this conjecture is more in the proof than in the statement. And in particular, just to give one example, if we take the special case of this corollary in which A is delta naught, just the free-living zero simplex, the point, then it's trivial to deduce a theorem of Lurie, which gives a characterization of the covariant equivalences over a simplicial set. Now, Lurie's proof of this theorem is very difficult. It uses the notorious straightening theorem, the proof of which is very difficult to say again. But like I say, it's a trivial consequence of the proof of Joyal's cylinder conjecture. And if you want to see how that goes, you can check out my paper. And on that note, I will say thank you for your attention.
Thank Alexander for a very interesting talk. Are there questions in the audience or remarks? That does not seem to be the case. How about our other participants? So if this proof answered all the questions and all, none are coming, let's thank the speaker again. And, okay, so Nicola Gambino asks, does your proof ever need to go down to simple combinators?
Nothing too heavy, but it's all in that analysis. Well, all the hard thing is going on in between this equivalence between Sil AB and this functor category. So moving things along this equivalence does involve various simple combinatorics, but it's all fairly standard, I would say. But it uses, facts, decompositions of, Horn inclusions as certain push-out joins and all that kind of standard stuff.
Okay. George, ask.
Thank you. Alexander, how general can it be? It's related to the previous question. Can you replace simplicial sets with something more general, maybe something extensive? Maybe dual to commutative rings where delta 1 is the polynomial ring, and you remember this was Gersten attempts of K-theory and so on. Have you thought about this?
No, I can't say I have. All the techniques that go into it are all very pre-sheaf-like, so it's really important that all the categories involved are pre-sheaf categories. And so the sort of generalizations I would think of to other sort of pre-sheaf-like models for higher categories. It's quite natural to consider versions of these kinds of results and constructions in the context of weak complicial sets as models for infinity n categories and so on. But I certainly haven't considered any algebraic examples.
All right, thank you. And very nice talk.
Thank you.
There was a question from the audience.
Thanks. Yet another related question, a little bit more concrete. In your definition of the category of cylinders, you could repeat the definition, but replacing the representable by any object in the underlying topos. What are the properties of the resulting category? I guess it won't be a topos, but maybe it is extensive.
I don't know. There's something very nice that's going on with, well, the structure of delta 1 is so simple that one has this nice combinatorial analysis of simplicial sets over it. So I can't, I haven't considered, I don't know, the first thing I would consider is replacing delta 1 with delta n, so just with another representable pre-sheaf. But I feel that there are certain, because there's two aspects to this. There's the purely combinatorial aspects, and then there's the homotopical aspects. And I feel that somehow both of those require this special choice of a base, even. But no, I haven't thought about more general basis than delta 1.
Okay, now it really seems that there are no further questions, and I don't mind sending this to the server. And we have a break.